So now that we've talked about concurrent programming conceptually, let's talk about how you can develop concurrent programs in Java. And I'll talk in a bit more detail about threads, what they are, what shared objects or synchronizers are, and what message passing is in Java. We'll also talk about traditional Java threads and modern Java threads, which are so modern that they aren't even part of the Android environment or even the off-the-shelf Java environment. But I'll tell you how you can learn more about them. They're in something called Project Loom. And we'll also talk briefly about some of the common concurrency hazards that Java programmers face in practice. So, what is a thread? Well, in Java, a thread is an object because almost everything in Java is an object. Not everything in Java is an object, but almost everything in Java is an object. Things like int and double with lowercase d are not objects. They're native types. So what is an object? Well, an object has methods and it has fields. And here are some of the methods. There's a lot of methods that are part of Java's thread class. Historically, each Java thread had its own unique ID, its own unique name, its own priority that could be set or changed, its own unique runtime stack, which is handling the method calls, or especially recursive calls, its own thread local storage, its own instruction pointer, and other registers to keep track of where we are in the instruction stream in the thread computation. We'll see that with Project Loom, this has changed. Project Loom is the name of this new improved version of Java that's part of something called early access release. It's not actually part of the JVM you get in production, but you can actually get access to this if you want to play with it. So traditional Java threads are now called platform threads in Loom, and there are new threads, new types of threads called virtual threads, which are so-called lightweight concurrency objects. We'll talk more about this. I will show you examples of this later. A Java thread can also be in various states, and there's a whole bunch of states. I'm not going to run through all the states right now. We will look at these states in much detail later. You don't need to know them at this point in any detail. But in a nutshell, when you create a thread, you start out in one state. When you start the thread, you go to a different state. And as the thread runs, different things happen. It can wait, it can block, it can timed wait, it can terminate. And that's how you keep track of where your thread is, what the thread is doing. And this is quasi-important to know because if you run a thread in the debugger, it'll tell you what state it's in. And that can be useful for debugging sometimes. Modern Java threads, like virtual threads, can also be in different states. They're somewhat different states than the traditional Java threads. And I won't spend much time on this, although you can watch this YouTube video if you want to learn more about Java virtual threads. As I mentioned before, threads interact by shared objects or message passing. And shared objects are used to synchronize concurrent operations via objects to ensure certain properties hold. And the key concept here in a nutshell is this concept of a critical section. And the synchronizers are typically used to ensure that only one thread is running in a critical section at a time. And so you come in, you have to wait to acquire some synchronizer. Once you've got it, you've got exclusive access in the critical section. You do your thing. You update shared mutable state, for example. And when you're done, you release the lock. And then the next thread that's waiting can get in to do its thing. That's a common form of a synchronizer. There's other variants, of course, we'll talk about. The properties that these synchronizers are trying to ensure are mutual exclusion, which means that interaction between threads won't corrupt shared mutable data, and coordination, which means that operations occur in the right order, at the right time, and under the right conditions. So mutual exclusion is meant to avoid this kind of a problem, race conditions where things crash into each other in memory locations that are being accessed simultaneously by multiple threads without being protected. And coordination makes sure things happen in the right way, in the right order. That's a slightly different thing. It's like, my metaphor is passing a baton. So you've got to make sure you coordinate. There's a lot of different Java synchronizers. We are going to cover all of these synchronized statements and methods, reentrant locks, atomic operations, semaphores, condition objects, barriers. By the time you're done with the class, you'll have learned about all these things, and you'll also have had a chance to try them out to implement the concurrent resource manager that we're using to dole out Palantir to beings in Middle Earth. So it's really a fun example of how to use all these different mechanisms. The other approach, as I mentioned before, is message passing. And this involves passing messages from one or more producer threads, which send the messages to one or more consumer threads, which receive the messages by some kind of thread-safe queue. And there's lots of different types of thread-safe queues. So as we'll see, there's array and linked blocking queues, and we'll talk about what their behaviors are, and we'll also look at the implementation, a couple different variants of implementations, including the ones that are in Java itself. There's a variant of the linked blocking queue, an array blocking queue called a priority blocking queue, which arranges the messages to be delivered in priority order. There's something called a synchronous queue. We'll talk just a little bit about that when we talk about the cached thread pool executor. And there's something called a concurrent linked queue, which is basically kind of a linked list that can have multiple threads adding and removing items from it simultaneously. I'll wrap up the discussion today by giving a quick overview of concurrent programming hazards. So these shared objects and message passing mechanisms we just talked about are designed to share resources safely to avoid concurrency hazards. So what is a concurrency hazard? We talked about some things like race conditions, which can occur when your program depends on things that may go awry if the threads don't run in just the right way because they're not protecting access to shared mutable state. So that's a concurrency hazard. If you want to see an example of a race condition, a program that's deliberately developed to have race conditions, just to show it, take a look at this code, which you can get in my GitHub repository. It intentionally induces race conditions due to the lack of synchronization between producer and consumer threads that are accessing a bounded queue. So it's actually kind of fun to run it. Bad things happen, and it's deliberate. And then I also have other examples, of course, that fix those problems. And we'll talk about those later in the class. Another problem, another hazard, are what are called memory inconsistencies. And the technical issue here is if you have multiple threads running on multiple cores and you don't use the proper synchronization mechanisms, then those different threads on the different cores will see different views of what should be consistent shared mutable state. So you might have a variable that's shared between different threads, and if you're not careful, they'll have different views. And I'll show you an example of this in a second. This is the metaphor to think about. You will learn through hopefully pleasant but perhaps painful experience. I use visual metaphors for almost all the concepts I describe. And so memory inconsistencies is kind of like transporter beams in Star Trek, if you ever watched Star Trek. If you don't have your transporter beam working properly, you'll leave half a person behind, which is not a good thing. If you're not a Star Trek fan, but you've read the Harry Potter books, you probably remember splinching. And that's when you disapparate, but you don't quite take all of you with you. You leave your nose behind, or your arm behind. So same kind of thing. You get inconsistent outcomes. Here's a very simple example that demonstrates this. This is a class called loop may never end. And we've got a Boolean that's a field called mdone, we set to false. And then we go ahead and note that this mdone variable is unsynchronized and mutable, meaning that it's not protected by any locks or synchronizers, and it's going to be shared between two threads. Here's the work method, and thread T2 is going to read the value of mdone. It'll be in what's called a tight loop, reading the value of mdone sort of obsessively until it's told that mdone is true, in which case it'll stop. So that's what it's trying to do. Down here, the stop work method is setting mdone to true, and thread T1 is going to write true to mdone. And what you would think would happen would be as soon as thread T1 writes true to mdone, that will cause thread T2 to be done. But that is not the case. And in fact, if you run this program, much to your surprise, you may notice that T2 may actually never terminate, or it may terminate much further down the road than you'd expect. And that's because the setting of the mdone field in this thread, in the absence of synchronization, will not actually propagate that shared mutable state to thread T2. Isn't that weird? So those are the kinds of things that you will run into if you don't use synchronization properly in multi-threaded programs. And that's very non-intuitive. You would not have this problem in a single-threaded program. Of course, in the single-threaded program, there'd only be one thing going on, so you'd basically be stuck in a deadlock spinning on mdone. But anyway, that's another story. Another problem that can arise is called deadlock, and this occurs when two or more competing threads are waiting for the others to finish, and thus none ever do. And you can see here, this is an example of this. We have thread T1, which owns lock L1 and needs lock L2. And then we have thread T2, which owns lock L2 and needs lock L1. And this particular problem will never resolve itself without some other higher level mechanism like a timeout to break the lock, break the deadlock, because they are very stubborn and they're stuck in what's known as a deadly embrace. So they'll never be able to get themselves out of this. So that's the end of our overview of how you can develop concurrent programs in Java. Of course, there's a lot more to it. But this is enough to give you some ideas of what we'll be covering. And we'll be looking at various programming mechanisms and frameworks for both threading and synchronization that deepen all these concepts throughout the course.